Welcome students to the another lecture on the course decision making with the spreadsheet. In the previous lecture, I have talked about how to formulate a linear programming problem. In this lecture, I am going to explain how to solve a linear programming problem. One method for solving a linear programming problem is using a graphical method. So, agenda for this lecture is graphical solution for a maximization problem. This is the problem which I have brought here, which I have taught in the previous lecture. Okay. A linear programming problem involving only two decision variables can be solved using a graphical solution procedure. So, this problem maximization of profit equal to 10s plus 9d subjected to, there are 4 constraints there. I will explain how to solve this problem using a graphical method. What is the graphical solution procedures? The graph will have a values of s on the horizontal axis and the d on the vertical axis. So, in the horizontal axis I have taken s, in the vertical axis I have taken d. Any point on the graph can be identified by the s and d values, which indicate the position of the point along the horizontal and vertical axis respectively. Because every point s comma d corresponds to a possible solution, every point on the graph is called solution point. The solution point where s equal to 0 and d equal to 0, this point is referred to as the origin. Because s and d must be non-negative, the graph in figure 1 only displays positive solutions, because the s is greater than or equal to 0 and d is greater than or equal to 0. So, we will not consider any negative solutions. For example, if you consider this point, say s equal to 200, d equal to 800, and if it is this point s equal to 400 and d equal to 300, this is the one solution point. The next stage is plotting all the constraint into the graph. So, let us see how to plot the constraint number 1, that is cutting and dyeing. So, I have taken the constraint number 1, 7 upon 10s plus 1d less than or equal to 630. To show all solution point that satisfy this relationship, we start by graphing the solution point satisfying the constraint as an equality. Even though it is less than or equal to sign is there, we will consider equal to sign. So, that is the points where 7 upon 10s plus 1d is equal to 630. Because the graph of this equation is a line, it can be obtained by identifying 2 points that satisfy this equation and then drawing a line through the points. So, how can we get the 2 point? When you in this equation, if you substitute s equal to 0, you will get a d point. So, okay, if you substitute s equal to 0, say d equal to 630. So, we got 1 point 0 comma 630. The second one, you substitute d equal to 0, you will get the value for s. So, when you substitute d equal to 0, the value for s is 900. So, we got another point 900 comma 0. Thus, the second point satisfying this equation s equal to 900, d equal to 0. Given these 2 points, we can now graph the line corresponding to the equation. So, we got the 2 point. Okay. Now, we can draw a line. Because all the points on the line satisfy 7 upon 10s plus 1d equal to 630, we know any point on this line must satisfy the constraint. So, all the point above this line will satisfy the constraint. But our constraint is less than or equal to 630. But where are the solution points satisfying? Where the constraint is having less than or equal to 630. So, how to identify which side of this this line satisfy our constraint. You have to take any point which is below this line and another point above the line. When you substitute, for example, I have taken arbitrarily 200 comma 200. You have to substitute these values into this equation. If this point is satisfied, you have to shade on the left hand side, that is towards the origin. If it is not satisfying, you have to shade on the outside this side you have to shade it. Consider 2 points, S equal to 200, D equal to 200 and S equal to 600 and D equal to 500, what I have explained in the previous slides. You can see from the figure 2 that the first solution point is below the constraint line and the second point is above the constraint line. Which of these solutions will satisfy the cutting and dyeing constraint? When you substitute S equal to 200 and D equal to 200, we are getting the values of 340. So, this 340 is less than 630. So, the point which is on the left hand side of this line satisfy our constraint. Because the 340 hours is less than 630 hours available. So, S equal to 200 and D equal to 200 production combination or solution point satisfy our constraint. Let us take the another point, S equal to 600, D equal to 500. When you substitute this, we are getting the value is 920, but the 920 is greater than 630, that is violating our constraint. So, the region which satisfy our constraint is on the left hand side, this region. If a solution point is not feasible for a particular constraint, then all other solutions point on the same side of the constraint line are also not feasible. If the solution point is feasible for a particular constraint, then all other solution points on the same side of the constraint line are feasible for that constraint. So, what is the point here is, suppose if you take any one point, if it is satisfying our constraint, right. So, this is less than or equal to, this equal to represents only the straight line. When you write less than or equal to, this shaded line which is shaded in blue color. So, what this point says that if any one point is satisfying on this region, so all other points below this line will satisfy our constraint. So, one has to evaluate the constraint function for only one solution point to determine which side of the constraint line is feasible. Obviously, we have to see which side of this constraint line is feasible, whether it can be either on the left hand side or the right hand side. In this figure 3, we indicate all the points satisfying the cutting and dyeing constraint by the shaded region. So, this region is the region which satisfy our constraint. So, this will be less than or equal to 630. Like that, the same way I have taken the another constraint, that is sieving constraint. So, this less than or equal to 600, this less than or equal to 708, less than or equal to 135. So, these points satisfy our constraint. If I superimpose all the constraint, I will get here this kind of figure. So, the area which is common for all the constraint is called feasible region. So, this is the region which is common for, which satisfy all the constraint. So, that particular region is feasible region. Why we are calling it as feasible region? Any point, if you take any point, that point will satisfy all our constraint. Feasible solution and feasible region. The shaded region in this figure include every solution point that satisfy all the constraint simultaneously. Solution that satisfy all the constraint are termed as feasible solutions, and the shaded region is called feasible solution region or simply the feasible region. Any solution point on the boundary of the feasible solution or within the feasible region is a feasible solution point. So, in this boundary this is a feasible solution point. Finding the optimal solution by trial and error. One approach to finding the optimal solution would be evaluate the objective function for each feasible solution. What is the meaning? Every solution is feasible solution. We can substitute in our these values in our objective function. The optimal solution would be the one yielding the largest value. Suppose if you take this is point number 1, point number 2. So, you will get Z1, Z2. Okay. If the Z2 is larger than the Z1, because it is a maximization problem, the Z2 is the point corresponding to Z2, maybe say somewhere S2 comma D2 may be your optimal solution. The difficulty with this approach is the infinite number of feasible solutions are possible. So, checking all the points and verifying whether which is the optimal value is a very difficult one, because one cannot possibly evaluate an infinite number of feasible solutions. So, this trial and error procedure cannot be used to identify the optimal solution. So, the trial and error solution will not be used. So, we are going to find out another method. What we are going to do? We are going to select some arbitrary value for our profit contribution. So, select an arbitrary value for the profit contribution and identify all feasible solutions S comma D that yield the selected value. For example, which feasible solution provide a profit of $1,800. So, I have fixed, suppose if I want to have my profit contribution is $1,800, what should be the value of S and D. These solutions are given by the values of S and D in the feasible region that will make the objective function. Solution for an arbitrary value of $1,800 of a profit contribution. Suppose I want to make a profit contribution of $1,800. Okay. So, this is the line of 10S plus 9D equal to $1,800. If I want to make this much profit contribution, I have to find out what is the value of S and D. So, because it is intersecting on the x axis and y axis, I can find out where it is intersecting. Otherwise, in this equation, if I substitute S equal to 0, I will get the D value. If I substitute D equal to 0, I will get the S value. So, that is 180 comma 0 one value, then 0 comma 200 is another value. This expression in simply the equation of a line, which one? 10S plus 9D equal to 1800. All feasible solution points S comma D yielding a profit contribution of $1,800 must be on the line. So, all the points that is the points means value of S and D will satisfy this our objective function, it is 1800. The procedure for graphing the profit or objective function line is the same what I have explained previously. So, when you substitute S equal to 0, the D will be 200. So, we got one point, this point 0 comma 200. Similarly, when you substitute D equal to 0, okay, you will get another point 180. So, this is a point of 180. So, drawing the line through these 2 points identifies all solution that have a profit contribution of $1,800. So, the graph of this profit line is presented in this figure. So, this line is our profit line. Because we have taken only one value, similarly I can take another profit contribution value arbitrarily 3600, 5400. Then I can plot this line 10S plus 9D equal to 3600, 10S plus 9D equal to 5400. Because the objective function is to find the feasible solution yielding the largest profit contribution, let us proceed by selecting higher profit contribution and finding the solution yielding the selected value. For instance, let us find all solutions yielding profit contribution of $3,600 and $5,400. To do so, we must find the S and D values that are on the following lines. So, these are the two lines, right. We have to find all the points which are in these two lines. Okay. Using the previous procedure for graphing the profit and constraint line, we draw the $3,600 and $5,400 profit line as shown in the graph. Although not all solutions points on the $5,400 profit line are feasible region, at least some points on the line are, and it is therefore possible to obtain a feasible solution that provides $5,400 profit contribution. When you look at this line, where it is, say this line, right, it is not covering, see this is covering only from this point to this point. This region is not covered by this line, but all the points in this region will satisfy your objective function. Can we find a feasible solution yielding an even higher profit contribution? Please look at the figure 8 and see what general observations you can make about the profit lines which are already drawn. There are 2 points. The point number 1 is the profit lines are parallel to each other. Look at this one, all the points are parallel to each other. Second one is higher profit lines are obtained as we move farther from the origin. So, when we move farther from the origin, we are getting the higher profit line. So, when you go this way, it may be 5,600, this may be something else. So, what are the 2 points? All the objective functions are parallel lines, and when we move away from the origin, the value of objective function is increasing. These observations can also be expressed algebraically. Let P represents the total profit contribution, that is a P equal to 10 S plus 9D. So, I am going to I am going to write this one y equal to mx plus c format, because I want to know what is the slope here, because D, this is a D, this is D, this is S, this is not S. So, if I write in this form, I can find out this is the slope of that objective function. What is that? 9 by slope is minus 10 by 9. So, when P equal to 1800, when you substitute in the previous values, you will be getting minus 10 by 9 S 200. When you increase P equal to $3,600, again this is the equations. So, what is the similarity we are seeing? Even though the value of the objective function on the right hand side is increasing, the slope remains constant, minus 10 by 9, minus 10 by 9, minus 10 by 9. So, this implies that the objective function lines are parallel to each other. So, the slope minus 10 by 9 is the same for each profit line, because profit lines are parallel. Further, we see that the D intercept increases with the larger profit contributions. Thus, higher profit lines are farther from the origin. That we have understood algebraically. Next, we will look at how to find out the optimal solutions. Because the profit lines are parallel and higher profit lines are farther from the origin, we can obtain solution that yield increasingly larger values for the objective function by continuing to move the profit line farther from the origin in such a fashion that it remains parallel to the other profit lines. So, what it is meaning? Suppose we have the objective function like this. So, when we draw a parallel lines and when we move away from these origins, so there is a possibility the value of our objective function will increase. However, at some point we will find that any further outward movement will place the profit line completely outside the feasible region. So, when we move away from the origins, right, we should be careful that we are not completely moving away from the feasible region, because solutions outside the feasible regions are unacceptable. The point in the feasible region that lies on the highest profit line is the optimal solution. Okay. So, what we have to do? We have to draw different objective function line. We have to keep on move away from the origin. At the particular point, the value will be highest. So, that corresponding point is your optimal solution. So, what we can do? You can take a ruler or the edge of a piece of paper and move the profit line as far as from the origin as you can. So, what you can do? You can move this way, you can move this way, you can move this way. What is the last point in the feasible region that you reach? So, this point, which is optimal solution, is shown in graphically. So, this is the point, extreme point is our optimal solution. So, what is this point? How we are getting this point? There are two constraints are intersecting. One is finishing, another one is cutting and dyeing. Okay. That two lines where it is intersecting, that corresponding point is called your optimal solution. When you substitute that optimal solution your objective function, you are getting your objective function as 7668. How to get that intersection points? So, there are two constraints. So, wherever the right hand side is 630, which one? That is a cutting dyeing constraint. Okay. So, from this 7 upon 10s plus 1d equal to 630, even though it is the less than or equal to, because I want to know the value of s and d, I am taking equal to sign only, not less than or equal to, because otherwise I cannot solve it. So, 7 upon 10s 630 minus 1d. So, from this if you find s value, s is 900 minus 10 upon 7d. Okay. This is our value of s. Okay. The another constraint which is intersecting is your finishing constraint. So, I have taken 1 by 1s plus 2 upon 3d 708. So, instead of s, right, instead of s I am going to substitute this value. So, that I have taken here. So, 900 minus 10 upon 7d plus 2 pi 3d 2 upon 3d equal to 708. So, what you can do, this 900 you can bring on the right hand side, it will become minus 192. So, the remaining is minus 10 upon 7d plus 2 upon 3d. So, d is common, you take on the left hand side, the remaining is minus 10 upon 7 plus 2 upon 3. When you simplify this, you will be getting minus 16 upon 21 d equal to minus 192. So, the d value at the end you are getting 252. So, we got the d value. When you substitute this d value into this s, you will get 540. So, the optimal point here is 540 minus 252, that is the where the two constraints are intersecting. So, this point. So, this point is 540 minus 252. How I got this point? When I, after drawing the objective function line, when I keep on moving away from the origin, I found the extreme right side edge is this one. So, this point is formed by intersection of two constraints. So, I have solved the two constraint to get this point. So, 540 minus comma 252. When you substitute this value, you will be getting $7,668. A note on graphic line. Suppose a company manufactures two models of small tablet computers. Assume that there are two models, one is assistant model, another one is professional model. Management needs 50 units of the professional model for its own sales force and expects sales of the professional tablet to be at most 1/2 of the sales of the assistant tablet computer. So, what the constraint enforcing this requirement is P minus 50, because this 50 is consumed by their own sales force and it cannot exceed 1/2 of the assistant tablet. So, less than or equal to 1 by 2a. When you simplify this, we will be getting 2p minus 100 less than or equal to a. So, this is a constraint. I need to plot it. So, substitute p equal to 0, you will be getting a equal to minus 100. So, this is the point. So, when you substitute a equal to 0, you will get p equal to 50. So, this is another point. So, what is the point you have to note is, already we have defined that the solution will be only on the positive side, but there may be a situation for drawing this line, you may get a point, that point may lie on the negative sides, but at the time of considering the feasible region you have to consider only the positive value of a and p. That is the point you should note it. There may be another situation, r greater than or equal to t. So, r minus t greater than or equal to t. So, that is r equal to t. So, that is this point where it is a 45-degree line. So, if r equal to 100, t also 100, that is the meaning, that is a way of drawing the constraint. Next, we will be explaining an important term in a linear programming model, that is the slack variable. Otherwise, it is another name is unused resources. So, this was the given problem. We got the value. What is that optimal value? S equal to 540, D equal to 252. So, in the constraint number 1, when you substitute it, the resources used is 630, but the hours available is 630. So, all the resources are fully utilized, that is unused resources. So, this slack variable for this first constraint is 0. Look at the second constraint, sieving constraint. When you substitute 540 and 252, the resources consumed is 480, but the available resources is 600. So, 120 unit hours not utilized. So, here the slack variable for the second constraint is 120. For the third constraint, hours required is 708, hours available also 708. So, unused resources is 0, the resources are fully utilized, that means there is a 0 slack values. The last constraint, hours required is 117, but hours available is 135, there is a positive slack variables. So, what is the meaning of slack variable in the linear programming context? The unused resources is called our slack variables. Thus, the complete solution tells management that the production of 540 standard bags and 252 deluxe bags will require all available cutting and dyeing, all available finishing time. So, that means there will not be any unutilized resources. So, in this department all the resources will be fully utilized because the value of slack variable is 0. While 600 minus 480, so 120 hours of sieving time and 135 minus 117, so 18 hours of inspection packaging time will remain unused. So, what we are understanding out of this 4 constraint, we have 0 slack variable for 2 constraint. For another 2 constraint, we have some positive slack variables. If it is a positive slack variables, in that department there are unutilized resources are available. So, 120 hours of unused sieving time, 18 hours of unused inspection packaging time are referred as slack for the 2 department. In linear programming terminology, any unused capacity for a constraint less than or equal to type is referred as slack associated with the constraint. So, in a linear programming model, if the constraint is the type of less than or equal to type, the corresponding unutilized resources called slack variable. Often variables called slack variables are added to the formulation of a linear programming problem to represent the slack or idle capacity. So, that slack unutilized resources has to be added in the linear programming problem. So, unused capacity makes no contribution to the profit because it is idle, that is not going to help for achieving your profit. So, thus the slack variable have coefficient of 0 in the objective function. So, when you introduce the slack variable, the contribution of that slack variable is 0. So, in our objective function that will have the 0 coefficient. After the addition of 4 slack variables denoted as S1, S2, S3 and S4, the mathematical model of the problem becomes like this. See that we have added plus S1, plus S2, plus S3, plus S4 and it is equal to sign. Because the contribution of this S1 is 0, so in our objective function the coefficient is 0 S1, 0 S2, 0 S3 and 0 S4. So, this is the value of slack variable. So, cutting and dyeing department 0 slack variable, sieving department 120, finishing 0, inspection packaging 18. Now, I will introduce another term called binding constraint. What is the binding constraint? We can see that the cutting and dyeing and the finishing constraint restrict or bind the feasible region of this point. So, this point. So, this point is formed by finishing constraint and cutting and dyeing constraint. So, this is restricting our optimal solutions, beyond which it will become not optimal. So, this corresponding constraint is called binding constraint. Thus, this solution requires the use of all available time for these two operations. What are they? Finishing and cutting and dyeing. In other words, the graph shows us that the cutting and dyeing and the finishing department will have 0 slack. For any constraint, if it is 0 slack, that constraint is called as binding constraint. On the other hand, sieving and inspection packaging constraint are not binding the feasible region. See the other constraint, what are they? This inspection and this sieving, not binding the feasible region at the optimal solution, which means we can expect some unused time or slack for these two operations. Which one? Sieving and inspection. The next one is the redundant constraint, another term. The sieving constraint does not affect the feasible region and thus cannot affect the optimal solution. It is called redundant constraint. I will go back, what is the redundant constraint? You see this one, the sieving, this constraint, it is not forming the part of the solution. So, this constraint is redundant constraint. Even though it is redundant, we have to keep in our LP model, because when the resources of any constraint is changing, so the redundant constraint may be a binding constraint at a certain point of time. Okay. So, even though it is redundant, it is a custom to mark that redundant constraint also. Okay students, in this class I have explained how to solve a linear programming problem using a graphical method. I have taken a problem, I have solved that problem using a graphical method. In that I have explained what is the feasible region, I have explained what is the optimal point and what is the optimal solution. Then I also explained what is the slack variable, then I have explained what is redundant constraint. In the next class, the same problem I will solve with the help of a graphical calculator called Desmos. After that, I will use Excel solver to solve this problem. Thank you very much.